Now let us start to revise or to summarize the last two chapters. The first one on continuity. So, continuous of function. So, you remember that if you define the definition of a continuous function, then we say that a function, a real valued function, a real valued function is continuous if for every epsilon positive there exists a delta positive such that mod of x minus x naught is less than delta implies that mod of f of x minus f of x naught is less than epsilon. So that was the definition, and we just change the mod function by that is the distance between x and x naught by the distance function dx on x and dy on y. So a function f from a metric space x to a metric space y is said to be continuous at a point x naught if for every epsilon positive there exists a delta positive such that for all x is in x, this condition holds good. And this condition is equivalent, here is you can see that this is equivalent to say that x is in x lies whenever x lies in the open ball, whenever x lies in the open ball with center at x naught and radius delta, we always the f of x, the image of this lies in the open ball with center f of x naught and radius epsilon. So that was the definition of a continuous function. And then we provided several examples of a continuous functions and the boundedness, the real valued function is bounded if mod of f of x is less than m, if there exists a constant m. And we proved that the first characterization is this one. So finally we proved a characterization of continuity function in the following way, that if x and y be metric spaces, f is a function from x to y, then the following are equivalent. That is to say, a function is continuous on x if and only if for every sequence xn converging to x implies that f of xn converges to f of x. Keep in mind, for every sequence xn in x, we are not saying that f of xn converges to x implies xn converges to x. We are saying that for every sequence xn in x, xn converges to x implies f of xn converges to f of x. Okay, so this is equivalent. This is equivalent. If this is hold, then the function is continuous. So all these are equivalent, and the function is continuous if and only if inverse image of open set is open. But we cannot say that the function is continuous if the image of open set is open. Okay. Similarly, the function f is continuous if and only if the inverse image of closed set is closed. Again, we cannot say that the function is continuous if and only if the image of closed set is closed. The third one, and then a function is continuous if the image of the closure of A is a subset of the closure of f of A. And we proved that the composition of continuous function is a continuous function. And then we provided several exercises, and we defined the Eurodgen lemma. So before the Eurodgen lemma, we defined that if A and B are two subsets of a metric space X. So if there exists a continuous function f from x to close interval 0, 1 such that the value of the function f, the f of x is equal to 0 if x lies in A, and the value of f of x is equal to 1 when x lies in B. Okay, then we say that the A and B can be separated by a continuous function. And then we define the Eurodgen lemma. We say that if A and B are two disjoint closed subsets of a metric space XD, then there exists a continuous function f from x to close interval 0 that separates A and B. That is to say, the value of f of x is equal to 0 for x is in A, and f of x is equal to 1 for x is in B. So this way we can prove, we can have the Urizen lemma. And then we prove that the continuous image of compact set is compact. Okay. So that was a very important result. So continuous image of a compact set is compact. And then several exercises. And then the next concept was the uniform continuity. So here is the important thing is that in the uniform continuity and the continuity, you see that we say that the function is continuous if for every epsilon positive there exists a delta. Okay, so it means that delta is depending on epsilon, and also it is depending on the point x naught, because we are saying the function is continuous at a point x naught. So this for every epsilon there exists a delta. Delta is depending on epsilon and point x naught both. But if it is only depending on epsilon but not only on the point, if the delta is working for any point, then we say that the function is uniformly continuous. So this we have defined. We say that the function f is said to be uniformly continuous. Okay, if this for each epsilon positive there exists delta greater than 0, delta depends on epsilon such that for every x and y this is less than this one. And we have seen that every uniformly continuous function is continuous, but the converse is not true. And we have also proved that if x is a discrete metric space and y is any metric space, then every function from x to y is uniformly continuous. Okay, and we have that if x is your compact metric space and f is a function from x to y, okay, which is continuous, and x is compact, then it is uniformly continuous. So every continuous function is uniformly continuous if the domain set x is compact. Okay, this we proved. And then we proved that if f is uniformly continuous, then the image of a Cauchy sequence is a Cauchy sequence. And then we had several exercises. And then we defined homeomorphism. Homeomorphism means a function f from a metric space x to a metric space y is said to be a homeomorphism. Okay, if f is bijective, that is 1, 1 and onto, and f inverse f both are continuous. Okay, so f is 1, 1 and onto, f and f inverse both are continuous, then we say that the f is a homeomorphism. And we defined several things, and we gave the characterization in terms of, so f is homeomorphism if and only if G is open, if and only if the image of G under F is open, F is closed, capital F is closed subset of X, if and only if image of capital F under F is closed in Y. So these are the characterizations of a closed set. Now then we have the definition of the open mapping. Is a function f from a metric space x to a metric space y is said to be open if and only if the image of open set is open, and it is called closed if the image of closed set is closed. And then we have several examples, and then we defined the equivalent matrices. So suppose D1 and D2 be two matrices on the same underlying set X, and then these two matrices are said to be equivalent if for every sequence Xn and point X in Xn in X, if the sequence Xn converges to X with respect to D1, if and only if the sequence Xn converges to X with respect to the metric D1. So every sequence is converging with respect to D1 implies that it is converging with respect to D2 and vice versa, then we say that D1 and D2 are equivalent matrices. And we provided the sufficient condition for two equivalent matrices, that was this one. Okay, this was the sufficient condition for equivalent matrices. And then we gave several examples. And we defined the uniform convergence of sequence of functions. So Fn be a sequence of functions from a metric space X to another metric space Y, and F is a function from X to Y. We say that this sequence Fn converges pointwise to F if for every epsilon positive and for all X in X there exists a positive integer n such that this is holds good. And now we say that the set is uniformly converges uniformly to F if for every epsilon positive there exists a positive integer capital N such that this condition holds good. Okay, and we had discussed in a very detail that the uniform continuity and continuity, the difference between uniformity continuity and continuity. Okay, and then there were several exercises and several results, and we also proved the Dini theorem. We say that if X is your compact metric space and F be a continuous function, Fn be a decreasing sequence of functions, that is equal to Fnx is less than or equal to Fn. Okay, sequence of continuous functions. If Fn converges pointwise to F, then the convergence is uniform. Okay, so this we have proved, and then several we have seen examples, exercises related to the uniform continuity and continuity. And then we defined the boundedness of a function because keep in mind earlier we defined a real valued function, the boundedness of a real valued function, that was the function is bounded if you have a function f from x to r. Okay, if you have a function f from x to r, then we say it is bounded if there exists a positive number m such that mod of f of x is less than m. But here if you have a function f from x to y, okay, but y is not r, okay, it is any metric space, then how we can say that it is bounded? So the function f is said to be bounded if the image of the whole S under f is bounded. So that is to say if f of capital X is bounded. In other words, if there exists a constant m real number such that for any 2 points in f of x, the distance between any 2 points in this set is less than or equal to m. And set of all points as set of all bounded functions is denoted by b x y. And we proved that if Fn is a sequence of bounded functions from x and y, then Fn converges to f with respect to the metric this, okay, if and only if Fn converges uniformly to f. And we also proved that this result. So here is we can say that now let us consider the sequence. So if x and y two metric spaces such that x is compact and rho fg is defined in this way, okay, then this rho is a metric on the set of all continuous functions from x to y. And we prove that not only this, if x is compact and y is complete, then this metric space Cxy with this metric rho is complete. This we proved. Okay, so there were many, and then we proved the Alzela-Ascoli theorem. So Alzela-Ascoli theorem says that finally it was So this was the final form, Alzela-Ascoli theorem, which says that let X be a compact metric space and A is a subset of CXRN. Okay, set of all continuous functions from a metric space X to Rn. So this set is compact if and only if it is closed, bounded and equicontinuous. So we defined the definition of equicontinuity and then we provided several exercises and we proved these exercises. And then in the last chapter, we defined the Banach contraction theorem. So before Banach contraction, we define the fixed point of a set, a fixed point of a map. So let X be a metric space and T is a self map. T is a map from X to itself. Okay, X to itself. Then the point X bar, okay, X is called a fixed point of T if T X is equal to X. Okay, then we have seen that a map can have a unique fixed point, can have more than one fixed point can have infinitely many fixed point and may not have any fixed point. So now the question is how we can check whether a metric space has a fixed point or not. So for that we defined the contraction map. So what was the contraction map? Contraction map this. So let X be a metric space and T is a map from X to itself. Okay. It is called Lipschitz continuous if there exists a constant alpha greater than 0 such that the distance between Tx, Ty with respect to D is less than or equal to alpha times the distance between X and Y for all xy. If alpha is equal to 1, then T is called non-expansive. If alpha lies between 0 and 1, okay, close open interval 0 and 1, then T is called contraction map. And if this is strictly less than dxy or x is not equal to y, then T is called contractive map. And this alpha is called Lipschitz continuous. And we have proved that. So the meaning is that contraction means if you have an open ball with center at x and radius r, and if you are taking this T and T is contraction, then it will shrink, it will go inside a ball with center at T of x and radius epsilon. Okay, so that was the meaning. And then we proved the Banach contraction theorem. Okay, that was the main result. So Banach contraction theorem says, and it is very simple theorem, we say that every contraction map, okay, every contraction map defined on a complete metric space has a unique fixed point. It's very simple. So it says Banach contraction theorem says that every contraction mapping defined on a complete metric space has a unique fixed point. And the proof was constructive, and from the constructive proof we can prove that the result, and not only this, we can also calculate the result, because the main idea was that to use to generate the sequence xn, okay, in the way that for each point, so you can generate the sequence in this way: xn is equal to txn minus 1 or xn plus 1 is equal to txn. So you can generate a sequence. So you can start from any point, okay, calculate the value of the function at mapping at that point, okay, and then continue in this way. So you will have a sequence of, and then you will see that this sequence will converge to a fixed point of T. Okay, so we have seen that if, of course, if T is not contractive, then there may not have any fixed point. This we have seen. And we have also seen several other properties, and we proved that if X is your complete metric space and T may not be complete, but T raised to the power m, that is to say the composition of T m times with itself is contraction. T may not be contraction, but Tm is contraction. Then even T has a unique fixed point. And here it was the example. If you define Tx is equal to 1 when x is rational, Tx is equal to 0 when x is rational, then this is not a continuous function and hence not a contraction map. But if you see that T square is equal to, this is equal to 1 and this is equal, but T square is a contraction. Okay, so T is not contraction, but T square is a contraction. And so, if X is your complete metric space and T may not be contraction, but T raised to the power m, okay, contraction, then T has a unique fixed point. Okay, now the question is, what will happen if T is not contraction, but it is contractive? Okay, it is contractive. Keep in mind, every contraction map is contractive, but contractive need not be contraction. So, what we have done, we have relaxed the condition and we impose some extra condition. The compactness implies that completeness, but completeness does not imply the compactness. Okay, so here we have, we put some extra condition here and we relax the condition here. Then, if X is your compact metric space and T is contractive map, T is a contractive map, then T has a unique fixed point and the fixed point can be calculated in this way. Okay, this we have proved. And then we provided a criteria by which we can calculate, we can check whether the real value differentiable function is contraction or not. So, let X be a closed interval AB, okay, which is your metric space and with respect to the usual metric, and T is a map from the closed interval AB to itself, B continuously and differentiable on the open set, then T is contraction if and only if there exists alpha less than 0 such that mod of the derivative of T dash X is less than alpha. So, that was the criteria by which we can see whether whether a function from the closed interval AB to itself is differentiable continuous function is contraction or not. Okay, then we provided several exercises and some applications. So, we provided the application of fixed point theory to system of linear equations and to differential equations and to integral equations. So, then we finished and of course, we provided this some appendix and that is okay. So, here we stop our lecture and I hope that you have you enjoyed this course and you will do your best. Okay, thank you very much.